Thank you. Thank you very much. I'm very happy to be in Dubna for the second time. I have a good memory of my visit to Dubna 12 years ago. I remember very well that I met famous Russian mathematicians like Arnold and Anosov. Anosov has been one of my gods for many years. And I can even say that during many years that I even didn't know that Anosov was a human being. For me, he was a dynamical system. So when I met Arnold as a human being, I was really amazed to realize that mathematics is done by human beings indeed. So I want to tell you something today. I want to tell you the story of a theorem that took 10 years from the birth to the end. The end is a book that I will show you at the end of my talk. And the beginning was again 10 years ago and was during a meeting in the French Academy of Sciences. I was sitting next to Conceivage. And the meeting was really boring. It was not a mathematical meeting, it was administration. And as you might know, Conceivage is more interested by mathematics than by administration. And during the meeting, he was writing on a small piece of paper. He was obviously not looking at the meeting, not listening at the meeting. And all of a sudden, he passed me a subway ticket on which he had drawn this picture with only one word, and the word was impossible. And I want to start my talk explaining what he had proved during this meeting. It's a very small theorem. It's a very nice piece of mathematics that can be explained to most of high school students. So let me begin by explaining the content of the theorem. If you start with, let's say, 4 polynomials, real polynomials, P1 of x, P2 of x, P3 of x, and P4 of x, and if you assume that all the 4 polynomials vanish when x is equal to 0, you can draw the graphs of these 4 polynomials in the neighborhood of the origin. And you see a picture like that with one graph in pink, one other one is in red, the other one is green, etc., etc.
I'm sorry, Etienne, are you showing a picture because the title is still shown of your talk?
Aha. What's happening? What do you see? You see the title?
We see only the title and the PDF program.
So what should I do? 1 second. Huh?
I believe you are sharing only the application which shows the PDF. Perhaps the images are in another window.
Okay. Okay. Is it?
I think you should stop share and share your whole screen. This will perhaps solve the problem.
Okay, so I stop sharing.
And
then I should share again. Is it better?
We see now the word polynomials.
Okay, so that's the subway ticket that Conceivage showed me. So you can see only one word, impossible. And I was showing you
sorry, we are seeing just word polynomials. We don't see the ticket.
Oh, la, la.
So,
what should I do?
Yeah.
Now we see graphs.
What do you see now?
Graphs of the 4 polynomials.
Okay. You see the graphs?
Yes.
Okay. Okay. So I was saying that if you see all these polynomials, they all vanish at the origin. you can see that then when the graphs meet at the origin, they produce some kind of permutation. You see on the left side of the origin, you have the pink graph, which is the lowest one, and you have the red one just on top of it, then the green one, then the blue one, and then the purple one. And you see that all these colors from the left to the right, they are submitted to some permutation. And the theorem of Conceivage is that not all permutations are possible when some polynomials cross at the origin. And in particular, he showed that this permutation, 1, 2, 3, 4 on the left, and 2, 4, 1, 3 on the left, on the right, this permutation will never happen when 4 polynomials intersect at the origin. That's the theorem of Conceivage. So before we give the proof of this theorem, which is again not very difficult, I will show you that if you take 3 polynomials, you have 6 possible permutations a priori. And on this picture, you can see that the 6 permutations do occur under suitable choices of polynomials. You can see that the 6 permutations with very simple-minded polynomials are possible. For example, the identity can be obtained from the polynomials minus x squared, 0, and x squared, or the permutation 1, 2, 3 gives 3, 2, 1 is given by 3 lines, etc., etc. So if you have 3 polynomials, you have 3 permutations. You have a permutation, and all 6 possible permutations do occur. And the theorem of Conceivage is that this permutation, 1, 2, 3 gives 2, 4, 1, 3, is not possible. So let me prove that. The proof is very simple and I think very interesting, and I will show you actually 2 proofs. Let me begin by the most natural and simple one. Suppose you have 2 polynomials like x squared in red and 0 in blue. You see here that the permutation which is associated to these 2 polynomials is very simple. The red is on top on the left, is on top on the right, the blue is below the red on the left, and is below the red on the right. So the permutation is very simple. But if you take x cubed, then you have the switch. 1, 2 gives 2, 2, 1. And of course, the difference between these 2 cases can be easily understood using the concept of valuation. So here's a definition. Suppose you have a polynomial, P of real polynomial. P of x is ak x to the k plus ak plus 1, x to the k plus 1, etc. And you look at the integer k, the lowest integer k, for which ak is not 0. This lowest integer, I will call it the valuation of the polynomial p at the origin. And of course, you understand that if you have 2 polynomials, and if you want to know whether or not the graphs switch or do not switch at the origin, then the answer is very easy. You have to check whether or not the valuation of the difference of the 2 polynomials is even or odd. You see here the blue polynomial and the red polynomial. You see the 2 graphs switch at the origin, and they do switch because the valuation of the difference is 3. The difference between x squared plus x cubed and x squared has valuation 3. So in order to see whether or not you have this switch, you just have to look at the valuation of the difference. And the second tool that we need to prove the theorem of Conceivage is the following. If you have 2 polynomials like the red one and the blue one, and if you, let's say on the right of the origin, if the modulus of the blue is smaller than the modulus of the red, you can conclude from that that the valuation of the blue is greater than or equal to the valuation of the red, because the valuation gives you the dominant term of the polynomial in the origin, in the neighborhood of the origin. So if you know the valuation, you know roughly the size of the polynomial in the neighborhood of the origin, so that if the blue is smaller than the red, the valuation of the blue is bigger or equal to the valuation of the blue is bigger than or equal to the valuation of the red. Okay, that's all we need to prove the theorem of conceivage. Let's go on. Suppose by contradiction that we have 4 polynomials having this qualitative behavior in the neighborhood of the origin. So 1, 2, 3, 4 on the left, 2, 4, 1, 3 on the right. Subtract from P2, P3, and P4, subtract P1. So you will not change anything. The only new fact is that the polynomial P1 is now the 0 polynomial. So it's enough to prove that the picture in the middle of the slide is impossible. We have now 3 polynomials, F2, F3, and F4. And strictly speaking, we have a 4th one, which is the 0 polynomial, which would be F1. And I have to prove that this situation is not possible. Now look at what's happening. Let me call V2, V3, and V4 the 3 valuations of the 3 polynomials F2, F3, and F4. And let's look on the left. On the left, what we see is 2 is below 3, below 4. Therefore, the valuations V2, V3, V4 satisfy the inequality V2 is greater than or equal to V3 and is greater than or equal to V4. If you look on the right now, you see that the modulus of 4 is less than the modulus of 2. Therefore, the valuation V4 is at least equal to the valuation of V2 because of what I said earlier. So you see that already we know that the 3 valuations, V2, V3, V4, have to be equal by taking these 2 inequalities. Now, if you look on both sides, you see that the graph of F2 is crossing the graph of 0, which means that the valuation V2 has to be odd. Now, if you look at the graph of V3, of F3, you see that F3 is always positive, which means that the valuation of V3 is even. So we have 3 numbers, V2, V3, V4. They're all equal. One is odd and the other one is even. This is a contradiction. So this is the proof of the theorem of conceivage. And I must say that when I saw this theorem, I was really amazed to see that it is possible in the 21st century to prove a theorem about 4 polynomials, which is such a simple proof. Actually, Conceivage did not show me this proof. Maybe this is not his proof, I don't know. I can guess it is this is the simplest proof. But anyway, I was really amazed to see that it is possible, even today, to have beautiful new theorems with beautiful simple proofs. Okay, now immediately, as any mathematician, when you see a theorem, the first thing you want to do is to generalize it. And this is the obvious question. What's happening when you have not 4 polynomials, but you have n polynomials? And this is not difficult to see that, of course, there is a second permutation which is forbidden. On the left, you can see the permutation which is forbidden by Conceivage. And on the right, you can see the other permutation, which is the mirror image of the first one, which is forbidden by the very same reason. If you change each polynomial by its opposite, you get another impossible permutation. And it's a very simple exercise that you can do yourself to check that among the 28 permutations on 4 letters, 26 Yeah. Yeah. Victor wants to say something? No? So among the 28 possible permutations of 4 objects, 24 permutations.
24 permutations.
Among the 24 permutations of 4 objects, it's very easy to check that 22 are indeed possible, and that these 2 permutations that you can see on the slide are not possible, and they are the only forbidden permutations. And indeed, it was not difficult to show that, and I did that immediately the next day after meeting Conceivage, that if you take a permutation with n objects, and if you want to know if these permutations occur or does not occur for some collection of polynomials, I will say permutations of polynomial interchange. If you want to know that, it is enough to check whether or not it contains one of the 2 forbidden permutations of conceivage. You have to be careful when you use the word to contain. When I say to contain is an example here. You have here a permutation with 7 objects, and you see I drew in black 4 points, and you see that these 4 points are permuted in the same way as the forbidden permutation by conceivage. This does not mean that the 4 points are preserved by the permutation, but it is clear that if a permutation contains a forbidden permutation, then it has to be also forbidden by obvious reason. So the theorem that I proved, and it is very easy to prove actually, is that this observation of conceivage is the only counterexample. If a permutation does not contain one of these 2 forbidden permutations, it does occur for some collection of polynomials. So I was rather happy with that. And immediately I asked myself new questions. And the questions are more complicated. And what I want to tell you today is what I did concerning these more sophisticated questions. But before I go to these more complicated questions, let me give you another proof of the same theorem. This new proof is more complicated, but it will be a help for us for the more complicated question. So here's the other proof. Suppose you have a collection of polynomials. So on the left, I drew, I think, 8 polynomials. And you can see here 3 pictures which are illustrating the situation. On the left, you can see the 8 polynomials crossing at the origin, and you can visualize the permutation. On the middle, I drew equivalence relations. You have 8 polynomials, and you can say, well, let me put these polynomials in the same equivalence class if they have the same derivative at the origin. Then among these 8 polynomials, you can see on the picture that I have 3 classes: derivative 0, derivative minus 1/2, and derivative plus 1/2. And in each equivalence class, I can distinguish between them looking at the second derivative. You can see that the first equivalence class contains 4 polynomials. And this first equivalence class can be distinguished in 2 equivalent classes looking at the second derivative, etc., etc. So you can draw this subdivision of the set with 8 elements as subsets according to finer and finer equivalence relations. And on the right, I drew the same picture using some kind of combinatorial tree. On the root means the 8 polynomials. Then on the first level of my tree, 3 points corresponding to 3 equivalent classes corresponding to 3 possible first derivatives On the second level, you have 6 blue points, which correspond to 6 second derivatives. And then the lowest level, the deepest level, you have 3 additional points corresponding to third derivative. And you can see that these 8 polynomials are organized, are structured according to a tree. And the key lemma, you will see it's easy, but the key lemma is this. If you have a polynomial interchange, I claim that at least 2 consecutive integers in my permutations have images which are consecutive. Let's come back to the permutation of Conceivage. You have 4 points on the left, 4 points on the right, and you see that if you take 2 consecutive black dots on the left, their images are not consecutive on the right. And that's the key point. If you want to have a permutation which is eligible as a polynomial interchange, you must have at least 2 black dots which are consecutive on the left and whose images are also consecutive on the right. So let's prove that. Look.
Excuse me, can I have a small question? Do the order have to be preserved, or the order can be changed? They have only to be consecutive, but the order can be switched, right?
Of course, they could be. They are consecutive in the same order or switched. Of course, there is a possibility of switching. Look an example. Let me prove that. First, you take in your tree, you take polynomials which are the lowest level. So this means, for example, you have 3 polynomials. Let's take an example. At the lowest level, they have the same first derivative, the same second derivative, but their third derivative is different. So you have ax plus bx squared plus c1x cubed plus c2x cubed and plus c3x cubed. And you order the third derivatives, c1 less than c2 less than c3. Then I claim that if you want to compare these polynomials in the neighborhood of the origin, they are ordered like the main dominant term, c1x cubed, c2x cubed, and c3x cubed. And no other polynomial in the list f1, f2, f3, f4, f5, f6, 7, no other one can sneak in between the two, because this is the lowest level. If you had another polynomial going in between these 3, green, red, and blue, then they would be deeper in the tree. So if you look at the deepest part of the tree, you find 3 or 5 or 6 elements, whatever. You get some polynomials whose order is exactly like x cubed or x4, depending on the parity of the exponents. So if you take like the blue and the red, they are consecutive, and their images are also consecutive. So it's clear that if you take a polynomial interchange, you must have inside the black dots at least two which are consecutive and whose images are consecutive. Okay, now that we know that, how can we use it? Let me say something about graph theory. Very simple part of graph theory. Suppose you have a permutation of 1 to n. Associated to this permutation, you draw a graph. You take one vertex for 1 to n, and you connect I and j if the permutation pi reverses the order of ij. So on the left on my slide, you see 1, 2, 3, 4, and you see you see the permutation. 1 goes to 4, 2 goes to 2, 3 goes to 1, and 4 goes to 2. And on the right, I drew the associated graph with 4 vertices, 1, 2, 3, 4, and I connect, for example, 1 and 2, because in this permutation, 1 and 2 are switched. So every permutation gives a graph, and you have to be careful, many graphs do not come from permutation, and moreover, two different permutations might have the same associated graph. So the connection between permutation and graphs is far from being one-to-one. It's not injective, it's not onto. However, the graphs that we get in this way are very, very specific. So let me explain that. First, before I explain that, look at the graph associated to conceivage permutation. The graph associated to conceivage permutation has 4 vertices, 1, 2, 3, 4, and they are connected exactly like a chain of 3 intervals and 4 vertices. Okay. Now, let me explain something. Very simple. A permutation is a polynomial interchange that is associated with a family of polynomials if and only if the associated graph is a cograph. Now I should tell you what a cograph is. A cograph is a concept that has been invented in the 70s, basically by computer scientists. And the definition is very simple. I should first tell you what is a twin in a graph. Suppose you have a finite graph and 2 vertices. So one says that these vertices are twins if they are connected to the same other vertices. You see on my picture on the left and on the right, you have 2 vertices in blue, and these 2 vertices have the same neighbors. Yeah, they are twins. There are 2 kinds of twins. These twins can be connected or not. Yeah? So one says that the twins are true twins if they are connected, and false twins if they are not connected. So if you have a graph, there might be no twin at all. Typically, if you take a graph at random, there is no hope that you find two twins. However, here's the definition. Take a graph like this one. Try to look for twins. Look at this. The 2 blue vertices are twins. So if you find 2 twins, you delete one of them. You get a smaller graph. Now you look for twins in this new graph. You have 2 new blue vertices. They are twins, false twins in this case. Delete one of them. Look for twins. Here you find 2, and you go on. And if you can go on until the graph completely disappears, one says that the graph is a cograph. So a cograph is a graph that contains so many twins that you can disentangle him by successive deletion of twins. You start with your graph, look for twins, delete one, look for twins, delete one, and go on until you find no more twins. If the end in the final graph, if the final graph is just 1 point, one says that the graph is a cograph. Once again, this has been invented in the 70s for computer scientist reasons. Now, the theorem is this. This is a very simple theorem. You can prove it as an exercise for you. If you give me a graph and you want to know whether or not it is a cograph, and the answer is this. A graph is a cograph if and only if it does not contain this chain with 4 vertices and 3 intervals as an induced subgraph. So that's the key point. I remind you that an induced subgraph is a graph for which the distances between vertices is the same. So you should find 4 vertices for which the distance between the 2 endpoints is 3. So that's an exercise. Now, putting this together, it's very easy to prove that a permutation is a polynomial interchange if and only if its associated graph is a cograph. And using this fact that cographs are characterized by having no subgraph like that, you can prove that a permutation is a polynomial interchange if and only if it does not contain one of the two forbidden permutations of Conceivage. So that's another proof of Concavage's theorem. I agree that this proof is more complicated, but you will see soon that in the more complicated question that I want to discuss with you now, this approach is really the best. So you start from a permutation, you go to the associated graph, you look at the structure of the graph, and from the structure of the graph, you can deduce the criteria for being a polynomial interchange just from not containing one of the two permutations of Conceivage. Okay, so that's the end of the first part. Very elementary facts about polynomials. And now I want to go to the second part, which is dealing with curves. Immediately when I saw this theorem of Conceivage, 1 second later, I was convinced that for me, the more interesting question was not about polynomials, but was about algebraic curves. So let me explain first a few facts which have been well known for centuries now. This is the cover page of a famous book by Kramer. I don't know in Russia, but probably all French students know the Kramer's rule for linear equations. This is a wonderful book containing a huge number of beautiful pictures. And as you can see, if you understand French, that it is about the analysis of algebraic curves. And the purpose of Kramer is to draw pictures to understand the nature of algebraic curves, to draw pictures for algebraic curves. Here's an example of pictures that you find in his book. Kramer is trying to understand the local possibilities, how curves behave locally. Now, pages and pages of pictures like that, and he wants to draw pictures. You might know that if you look at curves of degree 1, actually there are lines, so it's not fun. If you go to curves of degree 2, you have ellipses, parabola, and hyperbola, and we know all of them. If you go to curves of degree 3, Newton has written a full book about them, giving a topological, he wouldn't use the word topological, but he described all possibilities of algebraic curves of degree 3. And he found, I forgot, 79 or a huge number of possibilities for the picture associated to a curve of degree 3. And here you can see pictures by Kramer, what he wants to understand what's happening in degree 4 and degree 5. He wants to understand the nature of a curve according to its degree. Now, what we know today is the following. If you take an algebraic curve, so it's something in the plane, it's a real algebraic curve, it's defined by some equation, P of xy equal to 0, and you take a point on it, and the main theorem, which is far from being obvious, is that if you look at the picture in the neighborhood of a point on an algebraic curve, it looks like that. It looks like a spider. You have the original point in the middle, and you have a certain number of half lines going out from it. And the key point is that the number of half lines going out from any point on the curve is always an even number. Every algebraic curve locally looks like an even number of points on a circle connected to a central point in the plane. That's a theorem which has, it's very difficult to say who proved it. Newton used it, Gauss claimed he could prove it. It's a long story, and the first proof in the modern terminology is probably from the beginning of the 20th century. Anyway, here's probably the most difficult slide in my talk. Let me remind it. So you have a ring. The ring is the ring of all power series in two variables, converging in a small neighborhood of the origin. This is a factorial ring. Any series like that can be written in a unique way as a product of power series, which cannot be written as a product of two elements. Irreducible elements correspond to irreducible curves. I will show you examples in a second. And the theorem, which again has a long story, is that locally an irreducible curve either is isolated, like for example, if you take the curve x squared plus y squared is equal to 0, it reduces to the origin, of course, in the real domain. Or it can be parameterized in the following way. X is plus or minus t to the n for some n, and y is a formal series, is a converging series in T. It's called the Newton-Peezer series. Forget that. I will show you some pictures.
There's a short question about the Newton classification, asking if, to clarify, there were some problems with this classification. Was it correct?
No, it was not correct. What I remember is that Kramer in the 19th century studied again the classification of Newton, and I think Newton had 70 something types of cubics, and Kramer found 140 something. So the classification of Newton was not complete. Moreover, the question is to know what classification means. In the times of Newton, it was not clearly established classification up to what? Today we would say up to homeomorphism. Homeomorphism of what? Today we would say up to homeomorphism of the real projective plane, etc., etc., etc. So the terminology was not fixed, but nevertheless, I will never say any negative word about Newton. Newton is a genius, and I would not say that he made a mistake. He made no mistake. He asked a wonderful question and he started solving the question. So the answer is yes, it was not complete. Okay? Oh, here's an example. Here's the curve x cubed is equal to y squared. It's called a cusp. And you see that you can parameterize it by writing x is equal to t squared and y is equal to t cubed. Very simple example. Here's another example. This is called a bifolium. You see the equation is written here. It's x squared plus y squared minus blah, blah, blah. And you see that this algebraic curve has a singular point at the origin. And at the origin, you can see 4 half-lines going out of the origin. Now, here's the tuck node. You have 2 singular points, one at the origin and one at 1, 0. At the origin, you have 4 half-lines. And at the point 1, 0, you have 2 half-lines. Here's another example. I like this one because at the origin, you can see 6 half-lines. And if you look at the picture in the neighborhood of the origin, you can try to parameterize it. As I said before, you can try to parameterize it using this Newton-Peezer series. Well, you can try to do it. It's not easy to do it by hand. So I do it using a computer, and here's the answer. The curve, which is here, locally, you can parameterize it by three formal series. You can see the yellow one on the bottom. You can see the green one, which goes from the left part of this kind of ellipse and going up on the right. And you can see the red one, which is on the right part of the oval and on the left part of the curve. So you see that when you look at the structure of the singularity, you can see three colors: the green color, the yellow color, and the red color. And these three colors, they define what we will call a chord diagram. Here's a chord. When you look locally, you can see a picture like that. This is a simple picture of a singular point on the plane. You have a singular point with a black dot, and you have curves here in green, red, and blue. So if you look locally, you see something like that. You see on a circle, you are seeing an even number of points. Here you have 2 red points, 2 blue points, and 2 green points. And these points are connected 2 by 2 colors. And so you get something like that. You get a combinatorial picture telling you about the nature, the local nature of the curve in the neighborhood of the origin. And this, we call that a chord diagram. So in the same way that a family of polynomials defined a permutation, in exactly the same way, an algebraic curve in the neighborhood of the origin defines a chord diagram. And when I saw the question of Conceivage, immediately I said to myself, now he understands permutations associated to polynomials. I want to understand chord diagrams associated to singular curves. So my question is, among all possible chord diagrams, can I distinguish those which come from some algebraic curve? Maybe all of them are. And that was my question that I wanted to solve. My first result that I got, I forgot maybe, but I thought about this question from time to time. I think I proved that maybe 2 years later. My first result was this one. If you take this chord diagram with 5 colors, and so 10 points on the circle, connected like on the picture, I proved that this is not associated to a singular point of an analytic curve. So somehow this chord diagram with 5 colors is similar to the forbidden permutation of Conceivage. So I said to myself, maybe I will find 1 or 2 forbidden chord diagrams, and maybe I can prove something similar to Conceivage, that the chord diagram comes from some algebraic curve, even only if it does not contain one of these examples. Except that at that time, I already knew only one example of a forbidden chord diagram. So that was my question. It took me a long time. And let me look at the time. Time is going fast. So I will go quickly through this part. You saw that when I discussed polynomials, I was using Taylor expansion. First derivative, second derivative, third derivative, etc. And I was organizing polynomials according to these derivatives. It turns out that when one wants to study algebraic curves, there is a tool, which is also very well known, which is similar to the Taylor expansion, which is called the blowing up, which enables us to organize algebraic curves according to derivatives, so to speak. So I think I will have to go very quickly on this part. Basically, it's going to look in polar coordinates. I am looking at my watch.
Our rules are not very strict, so
Yes, but I know 12 years ago when I spoke in Dubna, the time was 74 minutes, no?
Yes, but in Dubna, that's different because we have next lecture and so on, and here you're basically free.
So the thing is very simple. You write your equation in polar coordinates, and instead of looking at here's an example. If you take the curve x squared is equal to y squared, you have two lines crossing at the origin. If you look in polar coordinates, well, your two lines become two parallel lines because these two lines did intersect at the origin, but in polar coordinate, they arrive at the origin with different angles. So looking at polar coordinate is a very simple tool to delete the intersection, so to speak. And if you take, for example, our cusp, y squared is equal to x cubed, and if you look in polar coordinates, well, you have a similar thing that the curve which was singular at the origin, after looking in polar coordinates, it becomes a parabola. So the curve was singular and it's not singular anymore. And the trick is that if you do that again and again, it's a theorem of Noether, that if you take a singularity of a planar analytic curve, and if you look in polar coordinate that we call blowing up many times, after some time, the situation became smooth. This is somehow like the Taylor expansion. Anyway, if you take a singular point like this one, and if you apply this blowing up procedure, the thing is that you get something that I call a necklace of bands. Each time you blow up a point, you introduce a Möbius band. And if you do that many times, you get a very complicated necklace of Möbius bands. And you can analyze the chord diagram looking at this necklace. I must say that for me, it was very complicated. But nevertheless, I could prove the following theorem. I call that the fundamental lemma, which is very analogous to what I said before. If you have an interchange polynomial, there must exist two consecutive integers whose images are consecutive integers. The analogous statement is this. If you have a chord diagram that comes from a singular point, it must contain one of the following situations. It could be a chord which is completely isolated, like on the left, two black dots connected by a chord and nobody between them. Or you could have two parallel chords, which means, as on the picture, two chords which are indeed do not intersect and have nothing in between. There could be what I call anti-parallel, that they cross, that there is no other point in between. And finally, there could be a fork, like on the picture on the right. So I did prove the following. A necessary condition for a chord diagram to come from an algebraic curve is that it has to contain one of these four situations. So I was happy with that because then I could use that to produce an algorithm to decide whether or not a given chord diagram is or not coming from an algebraic curve. And the trick is very simple. You take a chord diagram, you look for one of these four situations. If you find this situation, if you do not find this situation, end of the game, your diagram does not come from singular point. If you find it, well, you delete the black, like on the picture. If you have two parallel chords, you delete one of them, and you go on. And if at the end, you finish with a chord diagram with no chord, then it is possible to find an algebraic curve. So I was somehow satisfied because I had an algorithm which was easy to program. So I did it on my computer and I did check on many examples. And I looked at the 9,749 chord diagrams with 7 chords. And I could find that among them, only 7,641 do come from an algebraic curve, and the rest does not come from algebraic curve. And that gave me the opportunity to find examples, more examples of diagrams which do not come from algebraic curves, like you can see here on the slide. I found 1, 2, 3 examples on the left. And finally, I could understand that the cycle with n chords connected like on the right are not coming from algebraic curve. So I was somehow happy with that, but not completely happy because I was not satisfied. I wanted something like conceivage. I wanted a characterization like a diagram is analytic, comes from an algebraic curve, if and only if it does not contain this or this or this. And so far, I did not have such a situation. I had examples of chord diagrams that would not come from algebraic curve. I had examples. I had a computer program. If you gave me a chord diagram with 15 chords, I could put it on my computer and I could get the answer immediately, whether the answer is yes or not. But I did not have a complete description of those diagrams which come from analytic algebraic curve. So I was half satisfied. But I was tired because I had been thinking about this question for many years. I had other projects in my mind, and I decided that I wanted to write down what I knew, and I wanted to write it down in a way that should be understandable, say, by undergraduate students. So my idea was to write down a book, hopefully understandable by students. I did it, and I asked a student from my university to read the first draft of the book. He read it, and he came to my office, Christopher, and he said to me, now he's my graduate student, but at the time he was an undergraduate, and he said to me, Etienne, I think you do not look at the problem in the right way. So he suggested that I look in a completely different way, and his suggestion was excellent. And I will tell you in a moment what was his suggestion. And from that, we got the final answer together. And actually the final paper was published last week because it took 2 years to be published in Asterisk. Anyway, so here's the suggestion of Christopher. Christopher said, okay, you have seen that you can encode a permutation by a graph. In the same way, you can encode a chord diagram by a graph. If you have a chord diagram, you can, on the top of my slide, you can associate to it a graph. Vertices are the chord, and you connect 2 vertices if they cross. So for example, in this picture, you have 5 vertices, and you see this is one of the forbidden chord diagrams, and you can draw this picture of the associated graph. And in the same way that we had a characterization of polynomial interchanges as co-graph, we had a theory of graphs which was ready and waiting for us, which had been created in the 70s, and which was really waiting for us with no more work to be done. So let me give you the translation of the fundamental lemma. Is translated in the following way. We had earlier the concept of twins. You can see here 3 graphs. On the 2 graphs on the left, you have 2 twins. And now I add a new concept, the concept of pendant leaf. The pendant leaf, you can see on the right, is a vertex which is connected to only one other vertex. Then the game now is, if you see 2 twins, you delete one of them. If you see a twin, if you see a pendant leaf, you delete it. And you ask yourself, if I do that again and again, shall I finish by destroying completely the graph? If the answer is yes, one says that the graph is collapsible. The graph is collapsible if you can delete it by, you can kill it by deleting successively twins and pendant leaves. So here's an example. This is a collapsible graph, and it turns out that these collapsible graphs have been studied in the 70s by many papers for very, very, very different reasons. No connection with algebraic curves, no connection with chord diagrams, only computer science examples. And they proved many equivalent definitions of collapsible graphs. Let me give you one. You take a graph and you take 4 vertices, 1, 2, 3, 4. Then you compute the distances. You have distance between x1 and x2, x1 and x4, x1, x3, x3, and x4. And then you add x1, x2 plus x3, x4, then x1, x3 plus x2, x4, and then x1, x4 plus x2, x3. So in other words, you compute the 3 lengths of the 3 diagonals. And it turns out that the graph is collapsible if and only if each time you choose 4 vertices, among these 3 numbers, 2 of them are equal. That's the definition. And this is equivalent to being collapsible. And finally, the most beautiful theorem due to Bandelt and Mulder is that you can characterize collapsible graphs by forbidden configurations. A graph is collapsible if and only if it does not contain one of the following examples. On the left is called a house, on the second one is called a gem, third one is called a domino, and the fourth one is a cycle. So you really have this wonderful characterization of collapsible graphs as being graphs that do not contain forbidden configurations. And if you translate that directly from the graph to the chord diagram, according to Christopher's suggestion, you get the answer to my original question. You get the following, because you have here examples of chord diagrams, and on the bottom you have the forbidden collapsible graphs, and get the following theorem, which is finally what I'm happy. A chord diagram is coming from an algebraic curve if and only if it does not contain one of the following configurations. 1, 2, 3, and the fourth one is not one example, it's an infinite family of examples because you have a cycle of length n. So I was happy with that because it's really the complete analogous to Conceivage. The only difference is that in the case of Conceivage, you have 2 forbidden configurations. Here I have an infinite number of forbidden configurations. Nevertheless, I was happy with that. Now, here's a summary of my talk, quickly. A singular point defines a chord diagram. Desingularization going to polar coordinates defines a necklace of Möbius bands. The chord diagram contains an isolated chord, a pair of parallel or anti-parallel chords, or a fork. This defines an interlaced graph, and this interlaced graph is collapsible, but the collapsible graphs do not contain houses, gems, dominoes, etc. If you put that together, you get finally the final theorem I wanted to get. It's a complete characterization of those chord diagrams which occur from algebraic curves. So in a way, I think that this theorem would have, I think Newton would have loved this theorem because it gives a beautiful, I think, a beautiful topological characterization, description of all algebraic curves in the neighborhood of a point. Okay, so I'm finished, but before I finish, let me mention something. Christopher went further, and he's good at computing, much more than I am. He knows how to compute combinatorics, etc. And he proved the following thing. Just to show you what he proved. If you denote by AN the number of admissible chord diagrams coming from algebraic curves, AN, and if you compute the formal series A of Z, sum of A and Z to the n, well, this formal series A satisfies this incredible algebraic equation. You can see here, Z cubed plus Z squared A to the 6, etc., is equal to 0. And this gives a very good estimate of the number of chord diagrams coming from algebraic curves when n goes to infinity. And for example, you have on the last line of this slide, you have the number of chord diagrams which are algebraic for n is equal to 1, 2, 3, etc. It's very easy to put on the computer. It's a very precise and algorithmic description of the algebraic chord diagram. And finally, I want to show you a theorem by Christopher also, which is the following. If you take an algebra, now if you forget about the local picture, and if you want to understand globally an algebraic curve in the plane looks like something like that. It's a complete mess. You have curves, and you have singular points, and in the neighborhood of each singular point, you have one of the pictures that I described earlier, and you want to count them. And you have many points, many singular points. For each singular point in the neighborhood of it, you have a chord diagram, and you want to put that together and to get an estimate for the total number of configurations. And here's an example of a theorem that Christopher got. I like it very much. If you give me the degree of a curve, let's say D, and you ask me how many topological types of algebraic curves of degree D are possible, not only smooth, but any singular curves, and you want to count them up to homeomorphism of the real projective plane, then this is an upper bound of the total number of possibilities of algebraic curves. It's 10 to the D squared. And this upper bound is a corollary of the previous characterization of chord diagrams. So I'm finished. There are many things to be done on the subject. Let me finish by giving one example, something I don't know anything about it. Take a surface in 3 space. F of x, y, z is equal to 0. Take a point on it, a singular point on it. It's a point in 3 space. Intersect it. Intersect your surface by a small sphere in the neighborhood of the origin. On this small sphere, you will see a singular curve. Question, which curves are possible? For example, exercise for you, the figure 8 is not possible. It is not possible to find a surface in 3 space such that if you intersect it by a small sphere, you find a figure 8 on the sphere. My question is, can you say something about the local picture of a singular surface in the neighborhood of a point? Now, to finish, I show you the book that was produced from that. This book was initially written in English. It was translated in Turkish. Then it was translated in Portuguese. And finally, it was translated in Russian. And Victor will tell me when it will be ready. I don't know. I didn't see it yet, but it will be available soon, I hope. Thank you very much. Thank you, everybody.
Thank you very much for very interesting talk. I really hope that you will come to Dubna, sure, maybe next year. I don't know. Okay. As for the book, it should be available in a couple of months, I believe. Good. In the autumn.